Okay, so let's do another problem here in which we have a mass sliding down an incline, and as it slides down the incline, it crosses a rough patch and then hits a spring. And so this mass is going to come down here, cross this, hit the spring, compress the spring, then come back. So I have several questions here. Okay, first of all, I want to know how far the spring compresses. Okay. Secondly, I want to know how high it is after it comes back. So I need to know the initial height. Okay, so let's say that the initial height is 1.65 meters. Let's say that the rough patch here has a length of 0.855 meters, so 85.5 centimeters. Let's say that the coefficient of kinetic friction across the rough patch is 0.204. Since we're talking about a spring over here, we're going to need to know the spring constant. So let's say that's 246 newtons per meter. Ultimately, we're going to need to know the mass of the block, so 356 grams. Okay, so there's the problem. Slide down here, cross the rough patch, compress the spring. So we want to set up that problem and figure out how does that work. Well, we're going to do this with energy considerations because we know that for this problem that we could find the speed before the rough patch. We could find the speed after the rough patch. For example, if we just do this part right here, we say that initial potential plus kinetic equals final potential plus kinetic, and so mg h naught equals 1/2 mv squared, solve for v. Okay, if we cross the rough patch in the middle, okay, then we know that u sub I plus k sub I plus the non-conservative work, because it is friction, equals final. Okay, we know the initial and final are the same, so 1/2 mv on the left side squared has to be related to 1/2 mv on the right side squared. Okay, the difference is the rough patch. Well, how much work do you do crossing the rough patch? Well, friction is opposing the motion, so it'll be minus F times L. So that's going to be minus mu sub K times the normal times L. Well, since we're level, to make the math easier, that makes mu sub K mgl. Okay, so minus mu sub K mgl. So we can solve for velocity in the right because we know the velocity there. Okay, then we compress the spring. Okay, so when we compress the spring, we know that before we compress the spring, u sub I plus k sub I equals u sub s plus k sub f. So before, we're going to say potential energy is 0, so it's going to be 1/2 mv squared. That's going to be the v right there. Okay, the final potential, or rather the final kinetic is 0, but the final potential is going to be 1/2 kx squared. Okay, and so we would use the velocity we found there, plug in there to solve. Okay, so that looks kind of complicated. Well, it looks complicated because it is complicated. And it's more complicated than it needs to be. So let me show you an easier way. Okay, so it slides down here, crosses the rough patch, and so compresses the spring. So I'm just going to do this all in one step. I'm going to say when it slides down here, we're conserving energy. So that means that all the energy conserved. We cross here, we lose a little energy, conserve energy, and then spring forces are conserved, so we conserve energy there. So I'm just going to do this all in one step. So k sub I plus u sub I plus non-conservative work right in the middle equals the final k sub f plus u sub f. Okay, so initially kinetic energy 0, so we started from rest. Final kinetic energy when we squeeze the spring is 0 because it stops. So the initial is going to be mg h naught. the non-conservative work turns out to be exactly the same. Mu sub k mgl, okay, equals 1/2 kx squared. Okay, and so we do it all in one step, and it's like, oh, wait, if we do it all in one step, that makes this easier. So now all we have to do is algebra. Okay, and so we do algebra and we solve here and we say, okay, x equals 2 mg h naught minus mu sub k l divided by k. Now let's check. Do the units work out? The mass, well, we had to convert that to kilograms. And then we got G, so kilograms times meter per second squared is Newton. In the denominator, we have Newton per meter, so that means that this comes out to be just meters. H naught is meters, L is meters, so meter times meter is meters squared. Oh, wait, it doesn't work. What happened? I forgot the square. So this should be square root. Actually, I didn't really forget. I did that on purpose. Okay, but that should be square root in there. Okay, and I did that on purpose just to prove to you that it's very important to take that extra step to go ahead and check your units. I noticed in the last test, a lot of people did not take that extra step to check their units, and had they done so, they would have caught a simple algebra mistake that was trivial to fix, and that would have saved them some points. So do that step. It's really important to do that step to check your units. Okay, so anyway, you do that, and we find the spring compresses 0.205 meters, so 20.5 centimeters. Okay, now, my next question. So this thing comes down here, squeezes the spring, and then it goes shooting back over here. So I want to know, what is this height right here? Now, we could have done the same thing. We could have figured out the initial potential energy here, find out how much it lost here, the speed here, find the energy here. That would work. There's nothing wrong with doing that. But I'm lazy, so I want to do this in as few steps as possible. Okay. So the fewest steps possible, I know that this comes down here, conservation of energy, loses a little bit of energy when it crosses the rough patch, comes across over here, squeezes the spring. This is all conserving energy. Squeezing the spring is conserving energy, converts it into potential energy. The spring converts it back into kinetic energy. All the energy is conserved, loses a little bit of energy a second time across here, comes back up here, and then comes to a stop. So I'm going to do this all in one step. Okay, so that means what we have is the initial potential plus kinetic non-conservative work in here. Okay, the final potential, final kinetic, and I'm going to say we start and end at rest. We start at rest, we end at rest. Okay, sorry, that should be UF right there. Okay, and so that means this is mgh naught. We lose 2 mu sub k mgl because we went over the thing twice this time. And then at the end, it's mgh1. Well, the m's and the g's all cancel. And so that tells me that h1 is going to be equal to h naught minus 2 mu sub kl. Okay, I plug in the numbers, and that comes out to be 1.3 meters. Okay. One more thing I want to ask with this problem. So thing starts here. Comes down here, bounces off, comes up to there. Goes back down, bounces off, comes back. Goes back down, bounces off, comes back. So I want to know how many times does it do this, and what direction is it moving when it finally stops. Okay. So how many times did it do it? Well, same thing. I'm going to say that initial equals final, starts at rest, ends at rest. Okay. So mgh naught minus n, that's how many times it went across, times mu sub k mgl equals, well, when it ends, it's at the bottom down here, so the height is 0. Okay. So I can divide through by m's, I can divide through by g's, then I do a little bit of algebra. So after I do some algebra, then I find that n is equal to h naught divided by mu sub k l. So when I plug in all the numbers, I get 9.46. So, well, you know, it's like how many times did it successfully cross it? Okay, it successfully crossed it 9 times because it stopped 46% across the last time. Okay, so so that way, that's telling me that it made it successfully across 9 times, and it stopped almost halfway across on that last trip. Now, the question is, what direction? Okay, so when n equals 1, look at what we got here. When n equals 1, it's going to the right. N equals 2, that's what we had when it bounced back. So n equals 3, the next time it goes, it's going this way. N equals 4, it's going that way. So n equals 5, going to the right. N equals 6 is going to the left. So what we know is that if n is odd, all the odd trips were going to the right, and if n is even, all the even trips are going to the left. Well, that means it successfully finished a trip going to the right. So it stopped part way going to the left. So that means the last successful trip was to the right, and it stopped as it was going back to the left. So it successfully passed moving to the right. It stopped moving back to the left. Okay. So that's this problem right here. So this is combining several different things, and then I'm also showing you a new technique, and that is combining all the steps together and just start to finish, and keeping track of everything, and then that can save you a whole bunch of steps. Again, that's the idea of how this energy stuff works. You can sometimes combine things and save a lot of steps.